So I'm going to consider an output function of a Cobb-Douglas type. I'm not going to like follow strictly some of the notation which is used in economics text or something, because I just want to illustrate some of the ideas which we talked about in the previous video with this actual functional form. Now you already know this, and this C is a positive constant. I'll just write C is positive, A is positive, B is, these are all fixed. L and K are positive, but they are variables. These are the variables. So it's a function of two variables. Now what kind of function is this? It's separable what way?
You multiply it.
It's multiplicatively separable. Okay, so we can use the sort of the ideas which we saw for differentiating multiplicative separable. But even if you don't need to know those. I mean, it just follows. This C is just a pain to remember. So, but I mean, you could just set C as 1 and simplify it. But since I wrote the C, I just use. So, what's the partial with respect to L? Well, so it's C A L to the L to the A minus 1.
K to the B.
K to the B. Or maybe I write F sub K is C
L to the A.
Times B. You can pull the B out, yeah. L to the A.
K to the B minus 1.
What is F sub LK, which is the same as F sub KL. And the general rule, as you remember, is you want to do both the differentiations independently, right? So this part you differentiate with respect to L, this part you differentiate with K and multiply. So you get CAB times
L to the A minus 1, K to the B minus 1. CA A minus 1, L to the A minus 2, K to the B.
Okay, that's good. So you just this part remains unaffected and this part just gets differentiated. That's how multiplicative separable things work. Okay? Each piece gets differentiated with respect to its.
That will be C B B minus 1, L to the A, K to the B minus 2.
Awesome. So we have all these partials. Now, so what can you now say about the signs of these expressions? Well, I assumed A and B are both positive. So I think you can say without much hesitation, and C is positive, this expression out here is positive for all L and K. L and K are we are assuming the factory owner. So by the way, this was, if you haven't seen the previous video, this was labor expenditure. And this is capital expenditure. Oops. Okay, and we're assuming that the person with positive expenditures in both the areas. Okay. Now here this derivative. What's the sign of this? Well, C and A are positive. L is positive. We are raising a positive number to any power. I mean, A minus 1 may be positive or negative. We don't care. But the point is, this is still positive. This is still positive. So overall, this is positive. Similarly, this is positive. So what this is saying is that the marginal product of labor is positive for all values of labor and capital. And the marginal product of capital is positive for all values of labor and capital. Okay, good. Now, what can you say about whether they substitute or complement each other? What can you say about this expression? Well, C, A, and B are all positive. What about this thing?
They are all positive.
They're all positive. In fact, because it's multiplicatively separable, that's sort of the reason why these sort of the signs don't really get changed. Effectively, what we're saying is that labor and capital are complementary. Okay, in a Cobb-Douglas situation, you always have labor and capital are complementary. In a multiplicative separable situation, each one is multiplying on the other, right? And because the coefficients itself are positive, that's complementary. That's the first interesting. Well, the second, if you say the marginal product being positive, is interesting, but that's sort of predictable. This is a special feature of this kind of function, right? Which means if you want to model a situation where they are not complementary, you probably shouldn't take a Cobb-Douglas production function. Okay. Now what about this one? What about the mixed? What about the not the mixed? This was the mixed one. What about the second order pure partial? What can you say on this?
If A is less than 1, then it's negative.
Then that means you have decreasing returns to labor. If A is greater than 1, you have increasing returns to labor, and if A is equal to 1, you actually have constant returns to labor, right? It would just be linear in labor and the second derivative. So this is related to the fact that, like, if you make the graph of x to the n, it's concave up if n is greater than 1, it's straight if n is equal to 1, and it's concave down if n is less than 1. So it's the same thing. Now you get that right? Yeah. Okay, what about the capital thing? Well, same story. Instead of A, you have B. Right? B instead of A. So the same story. Okay, now what about, so you see that in order to get increasing returns on labor, you really need the coefficient, the exponent on labor to be greater than 1. If you want to get increasing returns on capital, you want the exponent on capital to be greater than 1. However, what happens if you consider combined returns? So what do we mean by combined return? Well, suppose my total expenditure is E is L plus K. Okay, and now I fix L as a fixed fraction of E, and K as the remaining. So as the factory owner, I've decided that I'm always going to spend on labor and capital in this ratio, x is to 1 minus x. Now in that case, what's the output as a function of E? What's it?
So x to
C times
x to the A.
x e to the A, 1 minus x e.
to the B.
So that becomes C
X to the A by 1 minus x to the B by E to the x plus B.
A plus B.
Oh, sorry.
Okay, that's the output function. Now what do we mean? What do we see then? We see that the output function is, now if I ask you how does the output function, now what is sort of the combined returns output and labor, that really depends on A plus B. Okay, so if A plus B is greater than 1, what would that mean? What do you think that would mean if A plus B is greater than 1?
It means
If you keep x fixed, if you keep proportion fixed, you'll have
you positive combined return.
Well, increasing
rate of change,
returns
increasing returns
on, or sort of increasing returns on expenditure overall. Right? I mean, you could see this explicitly by taking the second derivative, right? All this is constant, and this you take the second on total expenditure. A plus B equal to 1, you have constant returns on total expenditure. And in fact, in like the real world Cobb-Douglas thing, people usually assume A plus B is 1 at the margin, because at the margin you do expect that you do get constant returns on total expenditure. Otherwise, you just keep spending more. And so there's some sort of sense in which this is sort of the case which should be the realistic case, the middle one. But since we are just doing it totally theoretic, sort of.
The realistic case should be A plus B is less than 1, right? You cannot just keep investing to the same scale and then.
Well, why not?
Not sure.
Well,
you just don't see like Mac companies. They don't expand to infinity.
Yeah, I mean, well, the way they usually try to do Cobb-Douglas, I guess they do it generally for those kind of factories which can grow to infinite size, not very real world. But when they do those things, they usually do the A plus B. So they sort of put that as part of the definition in some situations. And so that's why I said this Cobb-Douglas step. I'm not assuming this. But the point is that you see that now this condition, increasing returns on total expenditure, is a lot easier to achieve than increasing returns on either of them individually, right? So can you give some examples of values of A and B where you don't have decreasing returns individually but increasing returns combined? Like A and B are such that individually you have decreasing returns, but combined you have increasing returns.
Okay, so anything that's maybe 0.7 plus 0.5.
Yeah, so you can have A as 0.7 and B as 0.5. You would have individually you would have decreasing returns, and together you would have increasing returns. Okay. Yeah. So and that makes sense. That's sort of the law of diminishing, that you cannot you have to increase all your factors of production. You cannot just keep increasing one factor of production and expect increase. If you increase all of them together, then the general expectation is, and that's why I said the A plus B equal to 1 is sort of the general expectation. If your overall output should somehow be proportional to your overall expenditure in reasonable sized real world situations.